Hey, what's up guys? The purpose of this video is going to be for me to just work out some example problems for you, right? I think, the more practice you get, the better. So what I would suggest you do here is read the problem statement, right? Pause the video, try to work it out for yourself. And then, if you get stuck or want to make sure that you did it correctly, then you watch the rest of the video. I think that's probably the most beneficial thing to do here. Now, a few things to get out of the way. So this is, first of all, this is a homework assignment that I gave over the summer when I was teaching 175. It's mostly about the electric field, but if you understand the electric field, then I think the electric force is fairly easy to understand. And this is intended for my physics 476 students, but I think if you're in 175, it could also be helpful. I'm guessing that, judging by the number of views my last video got, that there are definitely non-476 students watching me do physics, and that's great. The more the merrier, tell your friends. So at any rate, I will say though, and I'm not just trying to get likes here, but if you find this helpful, then, maybe, honestly, I don't give a shit about my YouTube channel, but if you find this helpful, just give it a like, so then, I can sort of decide whether or not it'd be a good idea to keep making these. Okay, so let's begin here. The first one is, this is a pretty typical problem you'll be asked to do in lots of classes like this. So what we want to do here is basically, we just want to compare the Coulomb force, or the electrostatic force, whatever you want to call it, to the gravitational force, right? And there's kind of a point to this. We're going to see that the Coulomb force is much stronger, all other things being equal, right? So let's just do this real quick. We'll call the ratio of let's say the Coulomb force to the gravitational. I don't know why I capitalized gravitational. We'll call it R, right? So you might remember from physics 1 that, well, let's write out what the Coulomb force is first. And because this is going to go on top, right? This is going to be F E over F G. And we're doing this for 2 electrons, right? So what we can do is we can write K negative E, right? Remember, little e is the fundamental unit of charge, and that would be negative for an electron. It would be positive for a proton. So E by itself is actually taken to be a positive number. It's positive 1.6 or so times 10 to the negative 19th coulombs, but it's not going to end up mattering here because we're just comparing magnitudes anyway, right? Now, then the gravitational force between 2 electrons is going to be the gravitational constant, and then the product of the masses also divided by the separation squared, right? And this also kind of helps reinforce the idea that the electric force and the gravitational force share some commonalities, right? Because they both depend on some intrinsic property of the objects, and they both have this inverse R squared dependence, and they both act on the line that connects the 2 charges or masses. Now, the big difference between the electric force and the gravitational force is that the electric force can be attractive or repulsive, right? Maybe you think it's always repulsive. No, but okay, I'm going to do my best to not make any dad jokes. But so the electric force can always be, the electric force can either be attractive or repulsive. However, the gravitational force is always attractive, right? So those are some of that's really the big difference between the two. But, they also have a lot of similarities. So let's write this out, and I'm going to be very careful here because I'm bad with fractions over fractions, but we should expect this R squared to just cancel out and not appear in our result, because we're assuming that, in both cases, the electrons are the same distance apart, right? They could be a meter, they could be a nanometer, an angstrom, whatever, right? So anyway, what we find here is we find that our answer does end up not having any R dependence, right? And we find that it's just KE squared over G M squared. Okay. Now, you gotta bear with me for a moment here because I don't remember a lot of these constants. And I mean, in general, I'm not going to, you know, really work the numbers out, but I'm going to do that here just because I want to stress to you that, that the electric force is much stronger than the gravitational force. And I think seeing a number for that would help. So I'm going to use Mathematica here to get this number. The cooling constant is like 8.99 times 10 to the 9th, right? I do remember the charge. The fundamental charge is 1.602 times 10 to the negative 11th. Newton's gravitational constant, what is that? 6.67 times 10 to the negative 11th. We'll look it up because I can't trust my memory. Okay, cool. So it is 6.67 times 10 to the negative 11th. Oh, we have to remember to square this, right? So I will potentially make silly little mistakes like that. And, you know, I guess the point is don't completely blindly trust what I do, right? Question it. And I think the mass of an electron is that. It should be 9.11 times 10 to the negative 31st kilograms. Yep, that's good. Okay, so I remember some things. Now, let's just have Mathematica crank this out, and we see we get a huge number here, right? Actually, this is wrong because this is a typo. This should be to the negative 19th. Let's try this one more time. Just make Mathematica reevaluate it. So it's going to be 4.2 times 10 to the 42nd, right? That's freaking huge. So this should hopefully convince you that the electric force between two charged particles in general is much stronger than the gravitational force between them, right? And that's all there is to this problem. So just kind of a little bit of a warm-up. Okay, so let's just talk about the next problem here. What we have these wide, long plates, right? And in between, or in the volume of the plates, there's a uniform electric field, right? Which means that it's the same at every point. And so it looks sort of like I've sketched it here, right? It points straight up. And we have some electron that comes in with some initial velocity. And then as soon as it gets into this volume that's contained between the plates, it starts to experience the force, right, of the electric field. And so what we're going to end up having here is kind of like a projectile motion problem where this thing is going to come in and it's going to just sort of, its path is going to trace out a parabola, right? And what we want to do is we want to figure out how long it takes for it to hit the bottom plate. Okay, I think that should be clear here. So we start with the equation, this F equals QE, right? Now this is a vector, so let me just make it a vector. This is also a vector. And just to remind you, if I'm writing a vector, you know, I'll take the symbol and I will make it unitalicized and I will put it in bold. That's how I think a sensible person would type a vector, not with an arrow over it. That's fine for writing, but it's kind of gross if you're typing. So this is the equation that gives us the force on a charge in the presence of an electric field, right? And in this particular case, let me make sure the formatting is good here. What we have is we have that the force on this charged particle, which is an electron, right? So remember its charge is negative E, is this expression. Okay, this is our force vector. Now let's stop and take a second to think about what's going to happen here. So the electric field will exert a force on a charged particle that points in the same direction as the electric field if it's a positive charge, right? And that's actually contained in this equation here, because Q can be positive or negative, right? So we see that when Q is positive, this force points in the same direction as the electric field. But when Q is negative, it points in the opposite direction. And that's what we have here, right? Electric field pointing up, but we have an electron. So the force is actually pointing down. And this is perfectly analogous to what we did in physics 1 when we talked about projectile motion, right? So the key here is to use Newton's second law, right? And remember, this says that F equals ma, but we've also just found that F equals negative E, right? And so then what we have here is an effective acceleration that is going to be negative E over m big E, right, like this. And this points down. Right, so what we could write, something, let's see, we could write something like this. The y component of the acceleration is just negative E big E over m. Right, so big E is just the magnitude now, and that's going to be the 450 450 newtons per coulomb, right? And so then, you know, this is all well and good, but you might be wondering where to go from here, and it's perfectly understandable if you forgot, you know, kinematics, because kinematics is pretty forgettable. But we also need the kinematics equation. This one, right, that gives us the y position of an object as a function of time. And the way that I would write this is with a minus 1/2 gt squared. So what this means is that we're taking g to be positive 9.81 meters per second squared. So to sort of, you know, take a similar approach here, well, we could do two things, but I'm going to show you what I'll do. And I would suggest that you probably do the same thing. But obviously, right, this here implies that the magnitude of the y component of acceleration is just little e big E over m, right? Like this. So let's just take this information and plug it into this equation, right? And I'm going to use big T to symbolize the total time, right? Just to keep it separate from little t. And I'm going to go through and I'm going to say that this equals 0, right? Because we're solving for the time at which it hits the bottom plate. And so the final y position, if we take our y equals 0 position to be, you know, on this line here, is going to be 0, of course. And then the initial position, right, because this thing comes in, and as soon as it enters this region where the electric field exists, it's also at 0 height, right? So our y of big T is 0, and our y naught is also 0, right? Now, we have to, oh, I forgot a T here, God. Okay, we'll just pretend that didn't happen. We have to take this velocity that we're given and take its y component, right? Which means that we write v naught sine theta. And then what we're going to do is we're going to write, instead of writing 1/2 g t squared, we're going to use the acceleration that we found instead of g, right? So e over m t squared, okay? So if we clean this up a little bit, we find that 0 equals, I forgot the t again. Wow. Okay. I don't know. What am I doing? Okay, so, but at least I'm catching it. So anyway, just cleaning this up a little bit, we find something like this. And this is, you know, this is a quadratic equation, right? So if you wanted to solve this by hand, you would use the quadratic formula. Thankfully, Mathematica can do that for us. So I'm just going to tell it to solve this. And I'm going to be very careful when I type this in because apparently I am mistake prone. And I'm making more mistakes here. These should be big T's. I apologize for this, guys. I mean, you probably, honestly, most of you probably don't care, but it does bother me a little bit. Okay, this should be good. Right, because what we're saying, again, is we're saying that at time t equals big T, it is hitting the bottom plate. Okay, so I think that's fine now. And then let's have it solve this. And if you're familiar with Mathematica, you have to do this thing where you can't use capital E because that's a protected symbol. That is Euler's number according to Mathematica, right? That's like 2.718, whatever. So instead of using a capital E, well, I'll show you. If I put capital E in, it shows up in black as opposed to blue here, right? So that means that Mathematica already knows what that symbol means, like what its numerical value is. So what I would do is I would just hit escape or type a big E, and then the first thing that pops up is capital epsilon. You just hit enter, and there you go. You can use that, and it looks exactly like E, so not a big deal, right? Times t squared. And then we want it to solve for t. Now we should get two solutions here, right? Just as we did in kinematics. And we find that one is silly, right? It's just at time t equals 0, the electron is at 0 height, and that's just by hypothesis, right? But this is the useful one here, right? So we find that t should be 2 mv naught sine theta over little e big E, okay? And there you go. And you can do the numbers. I'm not going to do the numbers, but you know, yeah, I think you have all the numbers. You know the electron mass should be like 9.11 times 10 to the negative 31st kilograms. And everything else is given. So you should be set to do this. Hopefully that made sense. Maybe I should just talk about really quickly what would have happened if I had put a minus sign in here, right? Like that, which might be tempting because we did say that the y acceleration was this. And this is true, but this is also, remember, containing the direction. Okay, so if I had written this instead, which isn't going to work, I would have wound up with this whole term here, right? This whole term here being positive. And that just doesn't work mathematically because you can't say 0 is equal to something positive and non-zero plus something else that's positive and non-zero, right? So you don't want to put that in there, but I think if you did and you tried it, you would see that you get like an imaginary number or something, and imaginary numbers are usually not good for us. Okay. So hopefully that makes sense. The big thing here is just, you know, noting that there's a force on this electron and then also finding the acceleration, the corresponding acceleration. Now, we did not include the gravitational force here, right? And it would have been technically correct to include it, but we just saw, right, that the gravitational force pales in comparison to the electric force. So that's kind of the motivation for ignoring it. It really would not have made any kind of observable difference, right? But you could do it that way, and you would probably see that it doesn't really make any kind of difference. Okay, cool. So 3, this is not something that, you know, many 175 students will need, though I do think it's useful, right? Now remember that I'm gonna type big R instead, until I figure something else out, because it's hard to type a script R. I don't remember how I did it here. Type the big R instead of the script R. Is that a typo? That should be... Oh, I typed it twice, that's why, okay. So remember that this is just defined to be... Actually, not a ratio, it's just R minus R prime. And in this case, R is the vector that takes us from the origin, little r, right, is the vector that takes us from the origin to the point at which we want to calculate the field. R prime takes us from the origin to the location of the charge that's causing the field. And so this is a nice shorthand because it sets us up to basically automatically know the direction of the electric field, right? Because the direction of the electric field is going to point in the same direction as this R vector. But it isn't strictly necessary because you can always just use, you know, like sine and cosine and components and stuff like that, and that's also fine. But we'll just crank this out super quick. And for clarity, I am going to write this as a column vector instead of an ordered triple. And so we just subtract component by component, right? So the first component is 3 minus -1. The second is 4 minus 5. And the third is 5 minus 2, right? Dead easy. And when we go through and do the arithmetic, this should be 4. This should be, what, -1, right? 4 minus, yeah. And then 5 minus 2 is 3. Now, in the assignment, I asked my students to sketch the vector, or rather its projection, right, in the XY plane. So we'll just do this super quick. This is going to be probably a horrible sketch, but it's okay. Though it does bother me when I can't get these like lines perfectly vertical or perfectly horizontal. I have problems. Oh my God. Okay, I think that's good. And then we make a nice horizontal. Okay. And then this is going to have, let's see here. So this is going to, what was it? It's going to go 4 to the right. You know, the X component is 4, right? The Y component is -1. And so we go 1, 2, 3, 4, down 1. And so this vector should look something like this, right? And it's an arrow, so we'll give it a little arrowhead. Isn't that beautiful? But yeah, this is just kind of a simple math problem in essence. Okay, let's move on to number 4 here. This is probably what, you know, most classes have been focusing on is this kind of problem where you have multiple charges and they're you know, causing an electric field, and you need to figure out what that electric field looks like. So I've actually prepared, I think, a halfway decent diagram here. A little small, but that's okay. I think we can work with it. And we're actually just going to focus entirely on the diagram for the first, you know, half of this solution, if not longer. Now, I've color-coded the charges, right? So this one here, this red one, is the positive charge plus Q. That's at a comma 0, right? This one is a negative charge that's at -a comma 0. And this one is a positive charge that's at 0 comma -b. Okay, and what we want to do is we want to figure out the electric field at the origin, okay? So let's make a quick sketch here, try to convince ourselves what this might look like. Now, this charge here is positive, right? So it's going to generate, we'll call it Q1. That's what we called it, right? Q1. This is going to point to the left, like so, because remember that a positive charge will generate an electric field that points away from the charge. Okay. And that's that. You know, it's a good idea to try to get the length of the arrow that you draw somewhat reflective of, you know, the distance and the magnitude, but I'm not going to bother with the numbers here. So for me, it's not super important, but if you know that stuff, then it's not a bad idea, because, you know, making a good sketch will help you solve the problem, you know, more accurately, I guess. So that's that. Then let's draw an E2, which is going to be the charge or the electric field due to this negative charge. Now remember, the electric field due to a negative charge points toward the charge, right? Radially towards the charge. So this drawing is going to get a little convoluted, but it'll be okay, because I think we can all remember what it looked like originally. So I'm just going to draw another electric field vector like this, and we'll call this E2. So you might have noticed, right, that I drew these to be about the same length, and that's because each of these charges does the same thing at the origin, right? This electric field has the same magnitude as this electric field, and direction for that matter, because they're both at distance a from the origin, and they're both being caused by charges of the same magnitude, right? So this was Q2. And so you want to look for symmetries like this, because they'll save you some time, and some of the meaner instructors might actually, you know, almost require that you find a symmetry to be able to solve a problem in a timely manner. Others will just make it so that it saves you some time, right? But you want to be on the lookout for this, because it's going to be huge in this class. Now, let's talk about the electric field of this one. This is a positive charge, right? Even though it's at -3, it's a positive charge. And that's where this can get a little confusing. And remember that positive charges generate electric fields that point away, radially away. So we're going to draw this one in. And this should be, it should be like a straight line. I'm doing my best here. Like this, right? E3. And this would be Q3, right? So the combined electric field then is just going to sort of complete this right triangle that we've made. And I'm going to do my best to draw that in accurately. So it's going to look maybe something like this. And I'll just call this E. So I would say always, always, always make a sketch for problems like this, because the sketches can sort of tell you if you've made a mistake and like if what you're doing makes sense. So there's this then. I think this looks good. Right. Now, actually, as far as actually solving this goes, here's what I would do. I would say the net electric field at the origin has two components, obviously, right? An X and Y component. So the X component is going to be, and maybe I'll just write this out symbolically first, and then we can substitute in what we know. We could write something like K Q1 over R1. Though it should be negative. So what I'm going to do is I'm going to force it to be negative like this, because I've made my sketch and I see that it should be negative, right? And this should be squared. Okay, that's good. And then kind of a similar thing with the other one, right? We're going to write a minus sign in front, and we're going to force the sign to work out the way that we want here by using an absolute value symbol, or absolute value bars, right? Because if we had put that this was, let's say we had written this right without the absolute value bars, we would have a double negative, which makes it positive, right? And says that the electric field due to the second charge actually points to the right, which is not correct, because we know that the electric field points toward the negative charges. And then I'm going to put R sub 2 down here, squared. Now, putting in what we have, right, we have K that's a constant, it doesn't change. I think I just called it Q, right? Yeah. So it's either Q plus or minus Q or 3Q, right? So let's bring the sketch up again. Okay, so then this is going to be negative KQ. Now, R1 is just A squared, right? As is, or R1 squared is just A squared, as is R2 squared in this case. This is going to be K, and then I'll keep going with the absolute value bars for one more line here, over A squared. But then we find, right, when we sum this up, we get negative 2KQ over A squared, right? And this should be a negative number because we've already drawn our electric field vector and we know that its X component is negative, right? So this checks out because all these numbers, right, K, Q, A squared, they're all positive. And that's good because it's what we expect. Now, Y is a bit simpler because there's only one charge contributing to that. And that's going to be, we're going to write this KQ3 over B, or let's say over R3 squared, just to be consistent. But this becomes K3Q over B squared, right? Which is then, you know, 3KQ over B squared like this. So this is our electric field vector, right? And I'll write this out as an ordered pair. The first component, the X component, is negative 2KQ over A squared, and the Y component is 3KQ over B squared. You could get fancy and factor out the KQ if you want, right? That's something that we as instructors and TAs like to see, but you know, it's not necessary at all. And there you go, that's it. So if you wanted to, for instance, figure out what the magnitude of this was, we would use the Pythagorean theorem, right? And we would write something like E squared equals E sub X squared plus E sub Y squared, or alternatively, right, E equals the square root of this junk. I had a professor in undergrad who used to just look at all the algebraic expressions and just say, all this junk. I don't know. I have fond memories of that guy. So let's take this one step further and we can actually just crank this out, see what we get. Right, because solving for the magnitude is something that you should ideally be comfortable with, and it's not too bad in this situation. We do this, and then I can make Mathematica simplify this a bit for me, right? So I'm just going to have it do that. This is also good review for vectors, so vectors are going to be everything in this class. If you thought it was bad in first semester, oh boy. I mean, you're going to be fine. You just want to make sure you really understand vectors. So that's what we get. I wonder if I can make it simplify this for me. Make it a little cleaner. Okay, so this is what we find, right? And I'll just copy and paste this into the document. And that's one of the great things about Mathematica and Equation Editor is I can do that. So, you know, it goes through and it does the algebra, it simplifies things up, and this is what we find. We could even take this one step further, right? And we could pull the K squared, Q squared outside of the square root, right? Because the square root of the product is the product of the square roots. And we could just write this, KQ. Cool. Now, one more thing that you might want to think about is the angle that this makes, right, with, say, the negative x-axis. It's supposed to be theta. I won't necessarily go through and do this, but I'll just tell you how you might do this. The angle that it makes with the, and we'll say negative x, let's do this, negative x, x, okay. is found via, and we'll say that theta is going to be the arctan, right? Remember, we just take the arctan of the ratio. And this would be opposite over adjacent, right? So we would write this. We'd write E sub y. But we're going to write E sub... We're going to write the absolute value of E sub x here, or the magnitude of it, because I want to make sure that I get an angle that's between 0 and 90 degrees, right? And, you know, I can guarantee that by making sure that the argument of the arctan here, right? This thing, this is the argument, right? I can do that by making sure that it's positive. So you have to be careful about this too, right? Because these trig functions, they can do strange things, you know, if you put a negative value in, right? So this is just my way of making sure that I wind up with the angle that I've drawn in, okay? And this should be good. And then you can do a little sanity check here, right? If you go and you plug the numbers in, you should expect that it is somewhere between 0 and 90 degrees, right? So if you get a negative angle or you get something that's like 110 degrees, just go back and double check your work, right? But this should be good. Okay, so then now we're gonna do everybody's favorite, I think I just threw up a little bit in my mouth, integration, right? We all love integration, don't we? I'm actually embarrassingly bad at this, but I'm going to do my best here to show you how I would fumble through a problem like this. So I also have, because, and so while I'm bringing this up, I'm going to say yes, fumble, because like I'm literally just going to guess and then hope that my guess is correct. No, I'm going to check my guess, right? And that's the important thing. But, you know, you can just guess as long as you're going to go through and make sure that it's a reasonable guess, right? So here's the situation kind of that we're thinking about, and I really did my students a disservice here by telling them to take the left end point of the rod to be at x equals negative L over 2. I really should have just said take it to be x equals 0, because that's going to simplify things a bit here. So let's do that. Let's do it the easier way, because often you won't be told, right? I thought I was doing them a favor, but I don't think I actually did. So anyway, let's actually talk about what's going on here first before we start writing mystic equations. What we're trying to do here, right, is figure out the electric field due to a continuous charge distribution. So this is going to be different than the process for finding the electric field due to a point charge, because, you know, most importantly, this way is going to involve integration. Because we can't just, I don't know, we could, I guess, if we had enough time and energy, just imagine that this is just a row of say protons or something, right? And then figure out what the electric field contribution is due to each one. But that's going to take forever. And that would just be a very, that would just be a sum with a large number of terms in it, right? So integration, in a sense, is going to make our lives easier. So this is the sketch here, and I'm just going to go through. I'm going to change the limits of integration is what these are going to be, really. And I'm going to say that this is now x equals 0, and this is x equals L, which is much more natural than what I suggested in this problem set, right? So let's do it like this. This is going to be way better. Now, how you go about this, or how I would go about this, is I would argue that there's some little bit of charge, an infinitesimal bit of charge, right? Let's draw it in red like this. This is just my little bit of charge here, right? So this is dq for an infinitesimal bit of charge, right? And this is going to contribute, you know, dE to the electric field, right? So if I go through, and I'm going to try to be good about this, but if I go through and I draw a line basically going from the charge to the point, then I can use that to help me draw what the vector is going to look like, right? And we'll make it thicker. It's going to look like this, right? This is going to be my electric field vector due to dq, more or less. and it is an arrow, and we're going to call this D E. Okay. Hopefully so far so good. And then what I want to say is that this is going to look stupid, but I'm going to write this, that this here, this point is x equals x. And what I'm trying to say here is that this is arbitrary, because what we're going to end up doing is actually integration with respect to x. And, you know, now with a sketch made, I don't even really need to refer to the problem statement anymore. So let's go through and just, how do I want to do this? Probably like this maybe. Okay, so let's remind ourselves of the different kinds of charge densities that we have, right? We have lambda, and these are pretty canonical symbols, right? So I'd imagine that even if you're not, you know, one of Dr. Hong's students, your instructor will use the same kind of symbol. This is going to be a charge over a length, right? So this is the linear charge density. And this is what we want here, right? Because we have some charge that's spread out over some length. We also, however, have a surface charge density, which is just a charge over an area, right? And you see how we're just going up in dimensionality here. This is going to be surface charge density. And then finally, we have rho, which is kind of like mass density. It's going to be a charge over a volume. And we will use all of these, right? I actually think that surface charge density will probably be the least utilized one of these, but these are all things that we should know, okay? So we see that we want to think about a linear charge density here, because this rod is sort of assumed to have like a negligible radius, right? We could think of it as basically being a very thin wire. So what we do is we write the linear charge density in our situation is exactly what I wrote there, right? It's lambda is defined to be Q over L. But notice that this allows us to write that Q equals lambda L, which allows us to write this in the infinitesimal form, dq equals lambda dl, right? And actually, let's write x, because the length of the rod is along the x direction, right? So the L is kind of, it's not a dummy variable, but it's better to write x here because we have to integrate, right? So you should see, you know, a continuous charge distribution and expect to do integration. And doing integration requires that you have a variable with respect to which you, okay, look. Integration requires an integration variable, right? So in our case, that's x, which makes sense. Now, maybe if this rod was oriented vertically, you would use y, that's fine. It doesn't really matter, right? Because it's just a variable, but we're going to use x here. All right, so then this is one of the first things you're going to want to do, right? The next thing is to determine R, right? Remember, this would be the script R if I could type that, but I'm using big R instead for the time being. Now, let's look at this little point that we've chosen here at X, right? And let's think about how we could write big R, which is the distance from the bit of charge to where we want to calculate the electric field, right? That's clearly the hypotenuse of this right triangle here. And so what I would say is we could write that R squared is just x squared plus h squared, right? Where x then must be in the interval 0 to L. Now this is your interval, right? This is the interval over which you're going to integrate. And you want to make sure that this interval is where the charge lives, right? So there's no charge beyond L, so it wouldn't make sense for me to integrate over an interval that is longer than L, right? In a situation like this, it probably seems, you know, simple and intuitive, but you know, you would be surprised how many times how many times I've tried to do an integral over some length or area or volume where there isn't charge, right? So you want to be careful about this. And what we do then, I think this seems like a good guess, right? But what I would suggest that you do is check this for limiting cases. And so for us, those will be x equals 0 and x equals L, right? And so let's just talk about this for a second. When x is 0, right, we expect R, big R, to be h, because when x is 0, we're right here, right? So the distance is just h. However, when we're over here on the other endpoint, we expect it to be the hypotenuse of this right triangle, right? The hypotenuse made by a right triangle of base L and height h. And so we damn well better find that that's what we get. So let's check this. So you can probably see that it's going to work out, I think. But x equals 0 gives us that r squared equals 0 squared plus h squared, right? Otherwise known as r squared equals h squared, or r equals h. And that's good, right? We can probably see that from the sketch. I don't know who's using the microwave so much out there, but I really need to move. Anyway, I love my roommates. They're wonderful people. So then let's check it for x equals L, right? What we're going to find here is that r squared equals L squared plus h squared, right? And this tells us then that r equals the square root of L squared plus h squared. And this is again true, right? Because we expect it to be the hypotenuse of this right triangle here. And I'll just draw it in real quick, but I think everybody probably sees. But this is what we're talking about, right? This. And this is definitely square root of L squared plus h squared in length. Okay, so it looks like this is good. But you know, you might have guessed something else, right? And that's totally fine. Like if you know, the instructor gives you, which they probably won't, but if they do, if they give you bad limits of integration, right, like I did to my students, you don't have to use those, right? Because your answer isn't going to depend on them if you set it up correctly, right? I shouldn't say it's not going to depend on them, but you can still get the correct answer if you choose different limits, right? And that's where, you know, practice comes in. So what I'll just say is, for instance, like what if I had chosen this point here, right? The left end point of the rod to be negative L, x equals negative L, right? And the right end point to be x equals 0. That's a perfectly valid choice. You can still make it work, right? But you're going to have to change your limits of integration. And that's kind of what I'm trying to say. But if you want, you know, you could always mess around with a problem like this and try changing the limits of integration and see if you can still get the correct answer, right? Okay, so then we're gonna have to do a little bit more work here, and I don't know that I'll take this to completion because I don't want this video to be longer than an hour. But what I also want to do is I just want to draw in an angle here, right? This is theta, because we're gonna need this as well. So then this is also theta. And for a 2D situation like this, we need to break the electric field component, or the electric, how do I say this? The infinitesimal electric field into its components, right? And so this is probably pretty straightforward by now, but what we could do is we could write that dE sub x is going to be dE cosine theta. And I'm actually going to put a negative sign here, right? Because we can see from our sketch that the x component should point to the left, right? So this is going to make sure that this is going to ensure that we get the directionality correct here. Y, there's no problem, right? Because the y component should be positive. So here we can just write dE sine theta, right? Like so. Now what we have to do is we have to figure out what cosine and sine are, okay? And I'll just say from the diagram, we can see that cosine of theta, remember, is adjacent over hypotenuse, right? So it's going to be x over r, but r is the square root of x squared plus h squared, right? And notice that this suggests that theta is not constant, which is indeed the case, right? Because your angle is going to change as you slide, you know, left or right on the x-axis, okay? Because your big R vector should always be pointing toward where you want to calculate the field, which means that your theta must change, and this suggests that it does, right? And notice that this is going to be a positive number because x is contained in the interval between 0 and L, right? And so again, I just accounted for the fact that I know the x component of the electric field is going to point to the left with a minus sign. I'm just kind of forcing it to be negative, like this. Now, sine of theta, right? Sine of theta is going to be a little simpler because you won't have a variable in the numerator, right? Because h is constant, so we can just do this. But again, remember, sine of theta is opposite over hypotenuse, so this is what our expression becomes. Okay, so then this suggests that, and I'm just going to copy and paste this part here to save a little bit of time. So I'm just going to replace the cosine of theta with what we found theta to be, or cosine theta rather, right? Which is this. And then I'm going to replace sine theta with what we found sine theta to be, which is that. And we're almost there, okay? So the last thing to do really is to come back to this and write out the electric fields. So I'm going to do this. I'm going to say dE sub x equals negative k dq. Let me fix that. Let me actually write this differently. I'm going to do this. I'm going to say negative k over r squared. Okay, I think I see how I want to do this. Negative k cosine theta dq, right? I like to have the dq at the end. And then we're just going to go through and we're going to substitute in what cosine of theta and what r squared is. And same thing for the y component. This is going to be k sine theta over r squared dq. Now notice that this has the same form as we'd expect for like the electric field of a point charge, right? We have k times some charge, which is our dq, and then we have that over r squared. Now these sines and cosines are just numbers. They have no dimensions, right? So they're not going to really affect our answer. They're just going to tell us how much of the electric field is pointing in the y direction or how much of it is pointing in the x direction, right? So the last thing to do then, and I'll just take this down a line here. Oops, not that. I feel like it should know what I mean, but there we go. Okay, and I'm just gonna fill this in, right? So this means that this is negative k. Now r squared was x squared plus h squared, right? So that's my r squared. Now my cosine of theta was this gross thing, right? And then we have to remember that there's a dq, but remember that dq is just lambda dx, right? So this is what we end up finding. This is what we're gonna have to integrate. Now, for this one, it's gonna be pretty similar. I'm gonna do the same thing basically. I'm gonna write k over x squared plus h squared. Now, the sine of theta was this. We found this, right, to be sine of theta. I just messed that up, didn't I? Let's fix it. Like so. And then we're also going to write lambda dx. Now it's tempting to write lambda dy, right? Because it's the y component, but remember that this little bit of charge as it slides along the x-axis makes an electric field here that has both x and y components. So you don't want to write lambda dy here, even though it is sort of tempting. I almost did it, right? You don't want to do that. So this should be good. Then finally, and I'll leave this for you guys to do because you can do it in Mathematica or Wolfram Alpha or whatever, right? All that's left is to integrate. So our final answer should be that the x component, okay, I'm kind of a mess. The x component is going to be the integral taken over x equals 0 to x equals L of the infinitesimal x component, right? Which is this nasty thing, right? So you crank this out, you get your answer. And then similarly for the y component, e sub y equals the integral from 0 to L of this, right? This is what we need to integrate. Now, there are some things you can do to simplify this for yourselves a little bit, and I'll show you what that looks like, right? I'm going to factor, hey, I'm busy. I'm going to factor out a negative k in front of the integral because that's constant, right? And this is going to then become, and I can actually, hey, I'm busy. What's up, dude? What was your question? Okay. It's going to be this. It's going to be negative k lambda and then x over x squared plus h squared to the power of 3/2 dx, right? And I believe that like all the instructors are basically going to give you tables of integrals, right? So like the antiderivative formulas on your equation sheet, or on the exam rather, or you could put them on your equation sheet, whatever. But the idea is that you shouldn't have to like crank out this integral from, you know, scratch, right? You should just be able to identify it as one of the ones that's provided by the instructor. Because, you know, when it comes down to it, this isn't a math class, this is a physics class. And let me just also put k lambda here like this. And then what we can do is we can write dx over x squared plus h squared to the power of 3/2, not 2/3, 3/2. Okay, so there you go. You make the computer, or you look it up on a table of integrals, right? Crank out these integrals, you just get that done. You can plug in numbers if you want when you're done, right? That's, I don't give you any numbers, but you can make some up if you wanted. And the last thing I would suggest is that you figure out what the dimensions of your answer are, because they should have dimensions. These answers should have dimensions of the electric field, right? It should look like kq over r squared. Actually, there is one more thing you could do. You could plug in that lambda is just q over L, right? That would also be a good thing to do. And then you might actually get some cancellation and stuff, because that's what it is, right? Because lambda is constant. That's why we were able to pull it out in front of the integral. Anyway, I hope you found this helpful. I can't guarantee there aren't any mistakes here, but you know, the approach is correct 100%, right? And you know, maybe just hit the like button if you'd like to see me do more of these videos, so I can kind of get a feel for if people are finding them helpful or not. All right, that's it.